Okay. Our final speaker is me. So I want to begin by just thanking everyone who has spoken at the meeting, the people who come as discussants, participants, for what I at least have found to be an incredibly fruitful event. I've learned a great deal. I've really enjoyed it. I felt that the discussions were very fruitful. I did have an ulterior motive in inviting you all here. And it was almost as if I planned it this way, which I didn't. But the talks sort of all fit together beautifully into sort of connect with what I want to talk to you about. That said, what I want to talk to you about is very much a work in progress. And so this is the Big Dig in Boston, which was on an ongoing construction project for like 25 years, and then recently collapsed. So I think it's probably a good metaphor for what I'm going to do. This is a talk totally different from any other talk I've ever given. It's entirely programmatic. It's very, very big picture. I feel like I'm sort of coming clean, like I am, in fact, a philosopher, despite the rumors. And please bear with me. Whatever, tear it apart. I'm not saying like don't do that, but like that would be helpful to me. But I feel that I'm going to talk about a lot of things that I think are important and need to be thought about very deeply. And I've done some of that work, but this is really big picture and programmatic. And so it's going to be, I'm not going to give arguments for very many things. I'm going to sort of describe views and then say some things about them. And so just go in expecting that. And I really hope that I'm under-promising to over-deliver and not over-promising what I'm going to in fact do. Okay, so I said yesterday that this meeting is in some sense a follow-on from the meeting that we held last March, and as you've seen, there has been a lot of discussion of themes that came up in March, but sort of more mathematical issues connected to these views. But the meeting has another kind of origin as well, which is that Thomas Barrett and I both gave seminars. Held seminars, organized, convened seminars in the spring on issues related to symmetry, structure, and equivalence. And in fact, many of the participants in my seminar, me and Clara on different weeks, went up and presented to Thomas's seminar. We read lots of Thomas's stuff in our seminar. And so this meeting is in some sense an opportunity for me and Thomas both to sort of bring together some of the people whose work we were talking about in those meetings. And in some ways, what I'm presenting is kind of a term paper for me from my seminar. So I'm gonna have sort of as my focus here symmetry. So my seminar was about symmetries. But as we're going to see, what I want to say about symmetries is really going to connect up to lots of other things about metaphysics of science and structure and laws of nature and the epistemology of physics and stuff like that. Okay, so some of you may know, those of us who are in the seminar certainly know, there is now a large literature on the status and significance of symmetries in physics. Sorry, that's a typo. It originally said in philosophy of physics. There are a lot of questions that get asked in this literature. What are symmetries? Are they to be thought of as properties of theories? Like, are they somehow like formal things that come along with theories? Or do they have a sort of pre-theoretic or more informal status? Are they maybe guides to theory construction? Do they have empirical consequences? Are those empirical consequences in some sense direct? Can you observe what the symmetries of a theory are? How do you distinguish between direct and indirect symmetries, empirical consequences? Are they stipulated or discovered? So there are some accounts of symmetries according to which we just say what the symmetries of the theory are supposed to be. In other people think, well, no, actually, like somehow we learn about symmetries, either symmetries of the theory or symmetries of the world in the course of doing physics. One idea that comes up a lot is the idea that theories with symmetries are inferior to ones without symmetries. This is connected, of course, to the things that Hans especially was saying yesterday, but others as well, about artifacts of representation and the idea that somehow symmetries are supposed to indicate to us that there's something extra, redundant, or artifactual in our formalisms. And then finally, how should we interpret theories with symmetries? Is there some special problem that arises for the interpretation of physical theories if they have symmetries? And of course, this is connected to Neil's talk, because, and this previous question, because I think tied up with the idea that theories with symmetries are somehow inferior is the idea that they're not offering us intrinsic representations or intrinsic characterizations of the structures that we wish to represent in the world. So I just don't want to talk about those questions. I mean, I have things I have to say about those questions that we'll get to eventually. Not in this talk, I mean, eventually in our lives. But instead, I want to suggest that there's kind of focusing on symmetries. I mean, symmetries are extremely important, they're extremely useful, but focusing on symmetries as our subject matter in philosophy of physics is misleading. And what I want to suggest is that the thing that we should really be thinking about is how we use structure in physics. And I want to suggest that successful uses of symmetry-based reasoning are unified not by some, unified definition of what symmetries are, or some argument schema that applies in all cases where symmetries can be successfully applied to draw some conclusion, or anything that's particularly about symmetries. But rather, they're questions about the relationships between different structures that we encounter in the course of our lives as physicists. They're questions about representational adequacy, about structural dependence, about the relationship between laws, about meaning in physics. Often they're questions about generalization of theories, relations between theories. Theories end up being a power for thinking about these sorts of questions, but for reasons that don't have something to do with symmetries having a special status in physics, but rather symmetries playing a certain kind of role in mathematics, or being useful for certain kinds of projects in mathematics. Okay, and so just to sort of condense all that down, what I want to argue is that we should not expect some kind of univocal account of symmetries in physics. I want to argue that all symmetry-based reasoning in physics is sort of context-specific, and the way in which we should think about those contexts is by reflecting on what structural relationships we're using the symmetries to elucidate. And then the second thing I want to say is that I'm just going to be bold, every case of successful or compelling symmetry-based reasoning in physics is more illuminating to pose the questions as ones about relationships between the structures in question, rather than ones about symmetries in the first instance. Right, so symmetries are part of our toolbox for answering questions. They're not sort of the front and center thing. Okay, so there's kind of a concern here that everything I'm going to say has been said many, many times before. Maybe it's even just like totally common knowledge. And I hope that's not true, but it's okay if it is. What's certainly true is that I'm really drawing on ideas that have been advanced by lots of other people. And so I'm certainly not trying to claim that any piece of this story that I want to tell is original. So, I feel that what I'm going to say is really influenced by Howard Stein, who, the way that he talks about structure I find very, very compelling, but also in some sense, all I'm going to do is say, we should be like, okay, so Howard Stein's first published paper is this paper Newtonian spacetime, which is very, very important in foundations of spacetime theories. It's a paper about Newton and Leibniz and foundations of theories of motion and what kind of spacetime structure we need in order to make sense of Newtonian dynamics. It does all sorts of beautiful things, including resolving the rotating bucket problems. He does not use the word symmetry in that paper, or if he does, he uses it once or twice in incidental ways. It's not a paper about symmetries. It's a paper about structure. He goes on later on to say a lot about structure in other places, although he doesn't really give a systematic account. Now, he also has a paper in the same volume as John Worrell's paper on epistemic structural realism, where that idea is introduced. It's his paper, Yes, But, where he argues that there's no difference that makes a difference between sophisticated versions of realism and sophisticated versions of anti-realism. And there, too, he advances a kind of structuralist view, drawing on things that he had done in other parts of his work. And so for a whole bunch of reasons, I think what I'm doing here is very much kind of an attempt to continue a certain kind of Steinian project. But like, there are going to be a lot of details here that are coming from lots of other people, lots of you specifically. The fact that your picture doesn't appear on this slide is more a question of the size of the slide than anything else. Okay, so good. I'm going to talk about structure, and then I'm going to talk about laws, and then I'm going to talk about symmetry. So first, let me talk about structure. So this is a paper that Stein published in the 1977 Foundations of Spacetime Theories volume, where, for instance, David has work on observational indistinguishability of spacetimes, and Howard has another paper on Leibnizian spacetime. It's a paper that people don't talk about very much because it is just an extract of a letter that he wrote to Adolf Grünbaum. I guess maybe, David, you were probably there. Did you just give a dramatic reading of the letter at Grünbaum Fest in Boston?
No, this developed over some time afterwards.
Got it. And in the letter, he references other letters that he had written to Adolf. Now, this is like a 30-page typeset letter, and this is just an excerpt from it. I don't mean this is just an excerpt. I mean the published 30-page thing is just an excerpt from the letter. He references other letters that he's written. And so I don't know if Grünbaum was writing back to him. But he says many very, very interesting things in this letter, and it really makes me wish that I had access to all of the letters. In fact, I think someone should publish a book of either the collected letters of Howard Stein or just the Stein-Grünbaum correspondence, like the Carnap-Quine correspondence. Because when I read this, I think, what could Grünbaum possibly say in response? Howard's just right. But I don't think that Grünbaum would have seen it that way. Okay, so there's this passage that I've highlighted here that I think gives you a picture of some of the things that he says. And what he says is, you, literally Grünbaum, it's not the reader you tend to think of the world in terms of things, primary substances in Aristotle's sense. I do not. I tend rather to think of structures and aspects of structure. And what he goes on to do is to talk about the sense in which general relativity describes the structure of space and time. And this is to be contrasted with the sorts of things that Grunbaum wanted to say, which were questions more about whether space-time is a thing, whether the metric as a thing gets to count as chronogeometric. And some of the questions that are being debated here actually end up looking very, very similar to things that have been debated much more recently in connection with the dynamical view of relativity. So it's kind of an interesting historical document for that reason. What I want to focus on is this idea that one should think about, or at least that Howard does, and so I take that to have normative force, that one should think about the world in terms of structure and aspects of structure. And so I think he's describing an instinct that one can have, sort of a tendency. I mean, he describes it as a tendency to think, like how to think about the theories that we're using. And so I want to say, look, this is an attractive instinct, one that many people nowadays want to endorse, but that it also invites philosophical errors. And I think a common but deadly error is to attempt a general definition of what structures are, to sort of try to begin by saying, giving an account of structures. And the reason I think that that's a philosophical mistake is because I think it's fundamentally anti-structuralist on this kind of picture that what we mean by thinking in terms of structure as opposed to in terms of things. Because what you're trying to do if you're giving a definition is say what kind of thing a structure is. And yet we see this all over the place, going back to Bourbaki and Suppies, Sneed, people like that who are trying to define what structures are in order to get started on talking about a form of structuralism. But we also see this, I think, in the sort of the partial structure stuff by Da Costa and French, or in some things that James Ladyman has done. And I don't want to do that. In fact, one of the things that I like most about David's Math for Structural Realism paper is this idea that math is already a theory of structures. We don't need another theory of structures. We've got a perfectly good theory of structures. Okay, so let's just understand what we're doing when we're doing math as theorizing about structures. And when we're doing mathematical physics, I want to say, we're doing something closely connected to this. I'll come back to that in a bit. Now, one place where I think I disagree with David, at least in that paper, although I don't think that he actually is going to object to this very much, is how does any of this connect up with logic, right? So if we're going to think about math as already being sort of a discipline that's about theories of different kinds of structure, how do we think about logic? Is that as an alternative to math for thinking about structure, or as a linguistic alternative to thinking about the world? And I want to say that that's not the right way of thinking about things. I want to say that at least mathematical logic is a perfectly respectable mathematical theory of a certain kind of structure. What kind of structure? Well, the structure of mathematical reasoning. So I want to think about mathematics as logic as mathematics applied to mathematics. Model theory as our best mathematical theory of a whole bunch of really important concepts about how math relates to the world, like satisfaction, interpretation, things like that. Again, I want to interpret it as a mathematical theory of some aspect of mathematical practice. I do think of the practice as being prior to any of these things, right? So I'm endorsing a kind of strong anti-logicism here. I think we do math. I'll say a little bit more about what that means in a minute, but we do math. And in the course of doing math, we begin to ask questions about how math works. So we do some more math, and we develop mathematical theories of how math works. And that leads to, more and richer mathematical work. And similarly, set theory here. I want to argue that set theory shouldn't be thought of even as a foundation for math in any strong, certainly no ontological or epistemic sense. I want to think of set theory as an important background theory of set structure, which turns out to be a really useful mathematical context for developing our mathematical theory of satisfaction, interpretation, and so on. We can build things using sets that then we can show, in a certain sense, realize the structural relationships that our other mathematical theories are trying to talk about. Now, I think it's important here that our mathematical theories are talking about structure. They can be talking even in application about structures in the world. Model theory is a kind of attempt to theorize about how that works, an attempt to sort of represent that kind of representational relationship. I don't think it's a situation where we start with some theory, with some axioms or something like that. We then build models, and now we have to take those models and somehow say that they're related to the world in some way. I don't think that model theory needs to sort of stand in this intermediate place. I want to say, look, we can just talk about structures. We can encounter structures all over the place. As an example, when I say that there are two cups here, I don't think that I need to be interpreted as saying there exists a set with two elements which is isomorphic to these two cups with regard to their cardinality or something like that, or is in a bijective relationship to these two cups. I mean, I think that there are just a whole bunch of facts about the physical world which are such that if I added another cup, I'd be applying a kind of successor function to the cups here. And in principle, I could keep adding cups. And I could take the cups away, and I could add the cups. All of these things are things about the cups, not about a model of piano arithmetic that stands in some sort of isomorphic relationship to a possibility space, an abstract possibility space concerning the cups. So I think that model theory is our best way of understanding, like of mathematically describing how all of that works, but I don't think it's an intermediate between the math and the world. Okay, good. So when I talk about structuralism here, I presented it as a structuralist instinct, and I invoked Stein. As I said, Stein wrote this paper published in the same volume as the Weatherall paper, but he was very skeptical about the meaningfulness of a realism, anti-realism debate. And I want to suggest here that I'm not going to be any less skeptical about that. I'm not describing a structural realist view in the sense in which that's been understood. Now, I mean, I tend to think that epistemic structural realism is right with a certain amount of nuance. And I can say why in light of some of the things I'm going to say later on about laws. I don't like ontic structural realism at all, because again, I think that it's like fundamentally anti-structuralist, because you begin by saying the things are structured. Like fundamentally what there is structures. And I want to say something different. I want to say that the world has structure. The right way of understanding what we're doing as mathematical scientists or in doing applied mathematics is describing those structures. That's the reason I think why it's the structural things that are most likely to be preserved, because they're the things that end up being closest to our actual epistemic practice in science. But I don't think that what we're doing is somehow even trying to describe a fundamental ontology of structures. Okay, so I think what I'm endorsing here is a kind of structuralist, like structurally inclined quietism, where I want to say that applications of mathematics and science involve attributing certain structures to the world. I want to say that those applications are consistently successful. The fact that those are consistently successful is evidence that the world truly has the positive structure in at least some sense, possibly approximative. I don't think that there's more to say than that, though. I don't think that there's anything added by saying, and moreover, the structures are real, or the fundamental thing is the structure, or anything like that. Okay. I just want to this is literally a screenshot of a slide of Carrie giving a talk. I mean, I think what I'm saying here is very, very much inspired by the things that Carrie has said recently about structuralism as a stance rather than as a particular doctrine or a set of claims about what the ontology of the world is. And in particular, she emphasizes that if structuralism is a stance, then you should think of it as a stance that one should foreground in metaphysics that the language of physics is mathematics. And so, I think that there's like a real nice compatibility here between the things that I'm taking from David and the things that Carrie said, and some of these Steinian ideas. I think that though I would advocate for a stronger view. Carrie, by the way, also says that ontic structural realism is false, which is, she has an argument for that. But in that talk, she just rejects that and then prefers this. So I think the kind of the quietism that I described was a view that, like, it's the successful application of math gives us reason to think that the world really has this structure. I want to say more about that because I think that is stronger than just highlighting the fact that we use mathematics in physics. I think that the way that applied math works is by using certain patterns of inference that are the ones that happen to be sound of mathematical structures. Like, so, we have a whole theory of how validity and soundness work, right? That also explains why certain kinds of inferences are truth tracking for certain kinds of mathematical structures, right? So, like, this whole cluster of mathematical logical subjects capture how all of these things fit together on the mathematical side. I want to say that, look, the fact that applied mathematics works is not just like a no miracles type argument. It's that in doing applied math, we're using these kinds of inferences that are truth tracking precisely when what we're talking about is structures of a certain sort. And the whole practice, it seems to me, depends on the idea that, in fact, the world is instantiating these structures in a sense that's well captured by the way in which models instantiate structure and inferences in first order logic, say, are truth tracking about those models. Okay, so this is getting me to a paper that I've been working on with Katie Robertson that comes out of some things that I've learned from other people. Partly Jill North, who talks a lot about perspicuity of representations, why some representations are better than other representations, is what got Katie and me thinking about this. But we're also inspired by some things that Tushar has said, and also Mauricio Suarez has said about inferentialism. Now, I don't really know what inferentialism means. I understand that Random talks about this, and everything I know about it I've learned from like 2 talks by Tushar, and so maybe I'm not even talking about inferentialism, but it seems like a pretty good word for the sort of thing that I want to be talking about. I also have up here Neil Dewar and Trevor Teitel, who are the people who I think are wrong about this. Because both of them, not Neil, I mean Trevor and idea that like anything can represent anything else equally well. And I think that you just cannot make sense of any of the things that we do, like literally any of the things that we do in our lives, like any of the ways in which our cognitive systems work or any of the kind of inferential stuff that we do, if that's the case. Neil thinks that there's no sense in which some representations are more perspicuous than others, but in the paper that he talks about this, he's really focusing on the way in which Jill tries to spell out perspicuity. And so I'm hoping that by the end of this 2-week visit, I'll be able to convince him that there are probably ways of doing this better. But the picture here is what I guess I began to sketch on the previous slide, that we should be thinking about mathematical structures being well suited, like particular mathematical structures being well suited for representing or being perspicuous as representations, precisely because the standard inferential systems that we're using to manipulate them are sound in that application. Like they really are tracking truth about the world. And I don't know what to, like, I don't think that there's any gap between that claim and the claim that the world instantiates that structure. Right? I think that there's just a very, very close link between what inferential systems are going to be truth tracking and reliable guides to say future evolution of systems or how to manipulate systems, things like that, and the world instantiating the structure that is being described and inferred about. Okay. So hopefully you both understood what I mean now by saying I'm not going to like give arguments, but also you have some sense of how I'm using the word structure and what kinds of considerations are going into this, how I'm thinking about it. Now, I think in the background is actually an even deeper story about the evolution of cognitive capacities. I think, you know, and this is connected to some of the things that David was saying yesterday, but I think maybe it goes a little bit further, although I don't think he's going to disagree with it. You know, we have evolved capacities for mathematical reasoning. We can represent stuff mathematically. We have, you know, a developmental process for acquiring number concepts, spatial reasoning, that we hone in order to develop more sophisticated mathematics. Now, there's a lot of learning involved in the more sophisticated applications of those capacities via practice and education. But I think of this as really just being a kind of inherited culture. We have a culture that has evolved on the basis of the cognitive capacities that we've evolved over, you know, our entire evolutionary history, that allow us to navigate the world and reason about certain kinds of situations. Now, I think that, like, you know, the education of a future physicist involves a lot of just transmission of that kind of often implicit information about how to use math to represent the world. And what I really want to emphasize is that we are never in a position that philosophers of physics like to imagine that we're in very often, which is we are presented with an uninterpreted mathematical structure, mathematical calculi, right? Something like what Hans was writing on the board yesterday. And now we're asked to like puzzle over what it could possibly mean and provide an interpretation from scratch of what this mathematical structures, like what the world would have to be like for this mathematical structure to be true or something like that. That's just not how it works. We learn how to do math and how to apply math over the course of like our entire developmental process from birth. And like we have to take all of that as part of our story when we're trying to understand how mathematical science works. Okay.
I could be before birth if you can keep listening.
Yeah, exactly. Yeah, even before birth, right? It depends on how you think about yourself. Okay, good. So having told you about structure, I will now turn to laws. So what are we doing? Let's see. I mean, what are we doing when we're trying to do mathematical science? So let me try to give a like very, very abstract characterization. Like, we're trying to identify in the world some things I'm going to call determinables, things that like can be one way or another. I'm thinking here of like stuff that we can observe, stuff that we can figure out how to measure, stuff that we can infer sort of must be there, must have some kind of influence on things that we can observe or measure, stuff that we bump into, interact with, engage with in the world. We're trying to find relationships between those things that permit certain kinds of inferences. This is extraordinarily abstract, I realize. But across different physical theories, what we're trying to do when we characterize a physical state is to just say, these are, these are some determinables, and this is what it's like to, this is how we specify them at a time. And then when we look at dynamical laws, we're trying to find relationships that constrain future or past values of these determinables, given some physical state at a time. Okay. Coming down just a little bit, we're not going to get to Earth, okay? Much of what we do is try to identify measurement theories for these kinds of determinables when we find them. And this is actually quite connected to what Neil was doing earlier today. And I'm very inspired. I think it's just like something in the water here in Irvine, insofar as there is any. Because Duncan Luce spent much of his career here and did a lot of foundational work on the theory of measurement. And what you find in that theory is that there are really deep and interesting questions that apply across the social sciences, but also apply in the physical sciences elsewhere, about the structures that we can use to represent the kinds of measurements that we can do when trying to make measurements of certain determinables. And so, what ends up happening in the measurement theory case, Simon and I were talking about this just the other day, it's often a little bit depressing. Like what you show is that if you look carefully at what you can actually measure, it turns out, and this is related to what Neil was saying, you can't multiply things, or you can't have averages, you can't do any statistical tests because there's not enough structure on the space of things that you're measuring to do that. But from a conceptual point of view, what we're trying to do is think about the structure of the ways in which these things we can measure can be arranged and how that relates to sort of our direct empirical access to them. In the case of physics, this is an extraordinarily sophisticated thing because we're trying to fit together a whole bunch of things that are often quite difficult to measure, which have complicated spaces of possible measurement outcomes. We're trying to fit them together in a broader mathematical framework as all being determined by a small number of variables, often ones that are not directly measurable, but which we ultimately seem to want to say are actual physical determinables that we just have to infer are there from things that we can measure. The stories about those relationships will often be very subtle. And the mathematics that we end up having to posit don't look all that much like the measurements that we're able to perform. But we're very good at this. We've been doing it for 400 years or so. What we end up with is equations and long stories, often with a lot of implicit knowledge about how to apply those equations in particular cases and eventually end up with some sense of possible measurement outcomes connected to this. Now, I want to emphasize here that there's a really strong modal character here. We're not looking for particular measurement outcomes. We're looking for the space of possible measurement outcomes. And we're not looking for particular configurations in the world. We're looking for the ways we're looking for collections of, I'll just say, we're looking for structure that determines these determinables in a, if possible, minimal kind of way, but also determines all of the ways in which they could be. Right? And so the activity involves much more than just trying to come up with a static representation of how the world is. Rather, it's trying to give a characterization of the ways in which the world could be and how those constrain one another. Okay, and I think I sort of said this already, but often in physics, the most useful relationships are ones where you're relating quantities from which many determinables can be determined, right? And so great example is the wave function in quantum mechanics. If you can figure out what the wave function is at a time, or you can figure out how it evolves over time, that then tells you what you should expect in a whole lot of different experiments that you could do. And you get this whole structure of observables that are connected to that. Okay, so it's these equations that I mean by laws. That's what I'm talking about when I talk about laws. I'm talking about those equations. These are structural relationships between determinables, structural relationships between determinables, which are then related to other determinables that we think we can measure. Here, I think, in my view, is the big question in the metaphysics of physics. along the way in doing this, we come up with some of these equations. In order for the equations to be coherent, to be meaningful, to be understandable as describing structures, we have to presuppose some stuff about how the world is. And I think that, like, the thing that we can do is try to say, as precisely as we can, what structure the world must have in order for the laws that we think accurately constrain, describe the evolution of the determinables that seem to be our best description and sort of the full collection of possible measurement outcomes that we could have to actually work. Okay, so here's an example. You might be familiar with this equation. I mean, I think of again, this is going back to Stein. I think that the Newtonian case is really fascinating, and for me is really the guiding example here. Because as Stein understands the debate between Newton and Leibniz, what's at issue is what do we need to assume about the structure of space and time in order for Newton's laws to make sense? And Newton thought, in F equals ma, I have a new kind of quantity that I'm introducing, the force, that I think is equal to or proportional to another thing, the acceleration. Now, the acceleration has a kind of meaning with regard to like the motion of bodies. This is not absolute. It had better be the case that it makes sense to say that this not like this, I'm sorry, this is absolute. This absolute thing is proportional to this thing, and so this also has to be not observer dependent. It has to be absolute in some sense. How can I make sense of absolute acceleration? And he thought that the answer was he needed to have a sense of place. He needed to have a sense of change of place over time, so absolute velocity. And he needed to have a sense of change in absolute velocity over time, which is going to be absolute acceleration. And so the way that I read Stein reading Newton is as developing a metaphysics of exactly this character, trying to say what, in particular, the structure of space and time have to be in order to make sense of full equations governing motion. So, you know, you guys say that Leibniz was a metaphysician. Newton was the one who was answering what I take to be the big question, the metaphysics of physics. Here's another example. It's Einstein's equation. I'm going to talk about the whole argument later on. I think that we can see in the history of relativity theory from like Einstein introducing the theory into the 1960s, a process of trying to condense, I mean, even this way that I've written it is like in light of a whole lot of work that's been done in understanding what the structure that's needed to make sense of this is, right? That you can write this down in coordinates, you can write this down as 10 couple differential equations, you write it this way. The fact that we end up at this is already a statement about what we think about the structure of the world. It has to be a space-time metric. There has to be a stress-energy tensor. This is the curvature. We have a whole story about how curvature relates to observable quantities. But the point is that in order to get to this, you know, it wasn't obvious when Einstein wrote this down in what sense he was relying on just a manifold and metric up to isometry. You'd really need to investigate the details of this equation, how solutions worked, what the initial value formulation looked like, what ended up being observable. I mean, Einstein himself, and working through the whole argument and getting to the point coincidence argument, was doing a lot of this work of trying to figure out what structure was presupposed and how to interpret, like how not to have too much structure such that you didn't know how to think about it vis-a-vis this equation. I think there are other questions here that make this discussion a bit less irrelevant to the literature on laws of nature. And so one thing that Neil and I have been talking about, and this is a different, more recent picture of Neil with no X through it. And something that Neil and I have been talking about for a long time is, I don't think that he knew that this is what we were talking about, but it is a question about what accounts of laws. I mean, among the extant accounts or maybe novel accounts that one might offer, can we say more about what laws of nature are to make sense of the kind of view that I've just described? The thing that Neil and I have talked about most directly is that Humean accounts don't do the trick because of the strongly modal character. And so the thing that Neil and I had actually talked about already was the idea that there's a kind of incompatibility between Humean accounts of laws and how working physicists think about what they're actually doing when they're like setting up experiments. I mean, there's a kind of counterfactual reasoning involved. Like, if the world were this way, it will evolve that way. That is not just working out retrospectively what the best system of the mosaic is. It involves a different kind of commitment to the relationships captured by the laws. And then Chris Mink and I have been talking about if we can say more in a sort of more richly historical way about this epistemology of physics and sort of fill in the details here. So there's a lot more work to be done, but that's kind of a picture that will now bring us to my discussion of symmetries. So, okay, first I just want to my sense is that the word symmetry in the philosophy of physics literature and in the physics literature is kind of a weasel word. People aren't super clear about when they're talking about, say, automorphisms or isomorphisms or something pre-theoretic. There's an idea that there's a kind of, to some extent, clear notion of what symmetries are that we're now going to give accounts of. I'm going to sort of specialize. I'm going to give a definition of what I mean by symmetry, but then I'm also going to break that later on in ways you'll see. So for my purposes, a symmetry is an automorphism. It's an invertible structure-preserving map from some structure to itself. The symmetries of some mathematical object are, like the symmetries of a group are the group isomorphisms from that group to itself. Space-time symmetries are, as JB said, isometries from a space-time to itself. Now, the reason I say this, I mean, I think that this is the mathematical definition of symmetry. I think it's a good definition of symmetry. If this is what we mean by symmetry, it's not always what people mean by symmetry, but if this is what we mean by symmetry, already we see that in any given context, we first need to say first what structure we're talking about, and second, what it means to preserve that structure. If you can't go in the opposite direction, because the symmetries are specifically the things that preserve a particular structure. Okay, so why care about symmetries? Now, this is not drawing on the literature. This is why I'm telling you should care about symmetries. Identifying structure-preserving maps associated with some mathematical structure or other is a crucial part of specifying what we're talking about when we're doing math. I mean, if you look at any math monograph, anytime a new structure is defined, the map that preserve that structure is also defined. It's just standard practice. That's how you say what you're talking about. I'll note, I mean, in many really interesting cases, there's more than one answer too for what the structure preserving maps are. A great example is in graph theory. When people try to use category theory to talk about graphs, you end up with 6 different categories of graphs because there's 6 different fruitful to graph theorists notions of structure preserving map or graphs. And talking about what it means to preserve that structure is doing the theorizing. Okay, so these structure preserving maps exhibit structural dependencies, right? And so there's just a really, there's a really sophisticated theory about this, but you don't need that to recognize the point. The issue is one where if I've got some structure and I've got some other stuff that depends on that structure, or that I want to know if it depends on that structure, one way to check is if every map that preserves the structure also preserves the thing that I think might depend on the structure. That's a pretty good hint that it does depend on that structure and nothing else. I say it's a pretty good hint for reasons related to Thomas's talk, because if you don't have enough structure preserving maps in a context, like if you have trivial automorphism groups, everything's going to be preserved by all of the symmetries, and so the whole thing kind of collapses. On the other hand, and this is why I said I was going to break my official definition of symmetry, in those cases, it's often perfectly good to just ask if things are preserved by things like the things that we're wondering if they depend on the structure are preserved by maps to other things that are also structure preserving. You know, it's like embeddings into some other structure, or even just well, I mean, I can give examples in Q&A, but the point is that there's a kind of necessary and sufficient character here, right? So if other things are preserved by your structure preserving maps, that gives you very strong evidence that they don't depend on anything that's not preserved by the structure preserving maps. And if they're not preserved by the structure preserving maps, that gives you evidence that, I'm sorry, I can't remember how I began the sentence. I think I'm going to move on. Okay, so model theory provides resources for making all of this precise in the first order case, right? We have a rich theory for rich first order theory of implicit definability and the relationship between implicit definability and explicit definability. We have these really interesting results that Thomas talks about in his "What Does Symmetry Tell Us About Structure" paper. There are many other philosophers that talk about it too, like Bet's theorem and Svenonius's theorem, that allow us to capture these sorts of intuitions precisely in the cases where we kind of have a rich theory available. But we also have great examples of people using this kind of reasoning in the wild. As Hans, when I was a graduate student, emphasized to me, this is what David Malamut is doing in the conventionality of simultaneity paper. Just using this idea that certain things aren't preserved by certain transformations, and so they can't be defined from the structure that's preserved under those transformations. It's a kind of application of this sort of implicit definability logic to cases where we don't have access to the full resources of first order logic. But as I said, it's also not just automorphisms. The thing is that what maps to consider and whether they carry enough information is often context specific. And so even here, I'm not suggesting that there's some recipe that's independent of context that doesn't require us to understand what structural relationships we're trying to probe. I'm just saying that what symmetries do for us is allow us to probe those relationships. Okay, so in practice, we see philosophers of physics impressed by particular kinds of arguments involving symmetries. And so the whole argument is one example, the gauge argument is an example, Leibnizian shift arguments, surplus structure arguments, and there are other ones. Given what I've said so far, you might not be surprised to hear that identifying the underlying inferential pattern, although this is in fact an ongoing research concern, turns out to be kind of elusive. And there are some people like Gordon Bellott, for instance, who will argue that there is no single formal notion of symmetry that can do all of the work that we want our symmetry reasoning to be capable of. And I think that that's right, but I think that the reason that's right is because the thing that unifies symmetry-based reasoning isn't a particular notion of symmetry or a particular argument schema, but rather the fact that symmetry is this really useful way of investigating structural relationships. Okay, so just to kind of be controversial here, what are some things that symmetries can't be? Well, symmetries can't fully characterize structure. I think the kinds of examples that Thomas and JB were talking about really drive this home. But frankly, this is something that David's been saying to me in slightly different terms since I was a graduate student, and it's just taken me like 15 years to. And he was talking about giraffes, and I think it's only recently that we had a picture of a giraffe that really drove home. You can see it in the paper that JB Thomas and I wrote. It's an idealized giraffe. I think it really gets to the heart of the matter. Symmetries can't be prior to physical theorizing. Now, on the other hand, like, this is another Steinian thing. Science as an enterprise is a thing that we're in the course of doing. And it's very often the case that we have ideas about what a theory should be, or a partial theory, or a theory that we know is wrong in some context, and we can use that with the theory, the actual symmetries that we encounter there, as a guide to further theorizing. But this doesn't happen sort of prior to any kind of theoretical conception of how the world works. It's not like we're presented with facts about what translations are like, and then from those facts about translations, we reconstruct like Newton's first law or Newton's second law or something like that, right? It's in the course of attempting to already say what the measurable quantities are and how they're related to one another that we realize that there are kind of mismatches between what we're assuming here and what we're assuming there, and symmetries are a really helpful way of sort of saying exactly what that mismatch is. And ultimately, I think that's what Leibniz is doing. Leibniz is saying, Newton, you have supposed this thing, but your dynamics have a symmetry that your space-time structure doesn't share. Leibniz is just using Ehrman's PS1 and PS2. Didn't know about it yet, but you know, it's you can reconstruct that argument too as sort of we're in the course of sort of preliminary physical theorizing, and we see a mismatch between two structures that we think ought to be related to each other. Symmetries can't determine what's measurable, observable, real. Like the nature of the symmetry to reality inference is not that there are symmetries and thus this is real. The symmetry to reality inference, in the cases where it's used, has a character that's much more like, we recognize that this structure is what's relevant to the dynamics as we best understand it. And that gives us a reason to think that this other thing, which is not invariant under those symmetries, can't be relevant to the dynamics. Because if it were relevant to the dynamics, the symmetries of the dynamics would be able to see differences in it. I think symmetries can't be arbitrarily stipulated. I'm not going to elaborate on that, but okay. So let me make some comments on symmetries of theories. So as some of you may know, the great philosopher Gordon Bellot introduced the principle of sufficient reason in philosophy in 2001. Here he is demonstrating just how large God had to make the world. Really big. So in this paper of Gordon's, it's a really fascinating paper. It's beautifully done. He makes a shift from arguments that philosophers have talked about a lot in the 60s about the principle of identity of discernibles and symmetry, to thinking about symmetries of theories as opposed to symmetries of objects. And then he goes on to say, well, when you have symmetries of theories, you have some sort of situation where maybe your theory has too much. Now, I think that there are cases, like there's a lot to this idea, but the way that it's gotten taken up since Gordon's paper, I think misses some important things. So that in order to speak coherently of the symmetries of a theory, you first have to say something about what the theory is. You need to give a mathematical formulation of the theory. What I mean by that is a characterization of like the whole theory as opposed to the individual situations that the theory describes. Now, Gordon does do that. Gordon uses Hamiltonian mechanics, and he talks about the Hamiltonian symmetries. And he argues that there are cases where you have Hamiltonian symmetries where you might want to move to a different formalism that doesn't have those symmetries. When we talk about symmetries of a theory subsequently, we don't always have a clear picture of what the mathematical structure that's representing the theory as an object is. So it's not really clear what we're talking about. And now, sometimes people do try to give formal accounts of the structure of a theory, including, some of the stuff that I've done using category theory. And one of the reasons why I think that stuff doesn't really work is I don't think that a category captures all of the information about a theory that it needs to in order for the structure preserving map from that category to itself to really count as symmetries of the theory. Because you aren't preserving all of the structure that you think has clear significance for the theory. Okay. And so the kinds of examples that are closer to working are things like variational symmetries, Hamiltonian symmetries. But something I'd really like to emphasize here is that in the context of real physics, the representation of a theory is really going to depend on the theory. I think there are very, very nice ways to do this for classical field theories in terms of differential equations defined as submanifolds of the jet bundle over bundles of field configurations. That is not going to work for quantum mechanics, and that's not going to work particularly nicely for point particle mechanics. Now, in point particle case, ordinary Lagrangian variational symmetries do a lot of the same kind of work. But the point is that how we represent the theory mathematically depends on the theory. Okay. So misnomers. Often when people talk about symmetries of a theory, they aren't really talking about symmetries of a theory in anything like the sense that I just said. They're talking about something that matters, but they're not really going to count as symmetries of the theory, or at least the sense in which they're going to be symmetries of the theory is going to involve a whole lot of extra machinery that it's not clear anyone has bothered to work out. And here's an example. People talk about diffeomorphism symmetry in general relativity. People will say that diffeomorphisms are symmetries of general relativity. Now, I actually secretly think that there's a way to make that idea precise. But it does not seem to be what anyone else has in mind. And in any case, they don't bother to tell us how you're supposed to present the theory of general relativity such that diffeomorphisms are maps from that representation of the theory to itself that preserve the thing that you said is the structure of the theory general relativity. And like the way that you actually use diffeomorphism, like that's not what happens. That's not what you're doing. Nonetheless, the fact that diffeomorphisms are symmetries of manifolds turns out to make them very useful for probing structural relationships in general relativity. And so it's not as if this isn't like a close cousin of symmetry-based reasoning, maybe just the sort of thing that we should count as symmetry-based reasoning. Okay, and so anyone remember the answer from yesterday's quiz? Are all diffeomorphism space-time symmetries? Never, no, never. Okay, so I'm going to conclude here with some remarks on the whole argument. Because I'm going to tell you why I think the whole argument is really, really important in the history of physics. And I'm going to tell you why you should all think that the whole argument, properly conceived, is really compelling as an example of symmetry-based reasoning. Here's a kind of definition. I mean, there's a real definition here. I'm not going to give it to you. I'm just going to tell you something. A system of partial differential equations is symmetric hyperbolic if it satisfies certain algebraic conditions. These are conditions on the equation, right? The equation be classified by whether or not certain tensors exist that satisfy certain equations. But there's an existence term. You're claiming that there exist certain things, which can, in practice, be very difficult to find. Here's a fact. If you do find the things that you need to satisfy these algebraic conditions to show that an equation is symmetric hyperbolic, you can then invoke a theorem that says if a system of partial differential equations is symmetric hyperbolic, it has a well-posed initial value problem. That's really useful. Here's a question that got asked quite often between 1915 and approximately 1960. Is Einstein's equation symmetric hyperbolic? And this is connected to what I said before. It was a really long and hard process of figuring out what Einstein's equation even was, much less the further process of figuring out what needs to be assumed about the world in order for it to make sense. And here, it turns out, is the answer to that. The answer is no. It is not symmetric hyperbolic. And we know it's not symmetric hyperbolic because if it were symmetric hyperbolic, it would have a well-posed initial value problem. But it doesn't have a well-posed initial value problem. The reason it doesn't have a well-posed initial value problem is that if you give me some initial data, the structure of the equation is such that if I take some open region, the future of that initial data, and I apply a whole diffeomorphism, I'm going to end up with another distribution of fields on the manifold. And the way in which we define well-posed initial value problem is if you give me initial data, there's then a unique configuration on the whole manifold that solves the equations. Now, part of the hard problem here is figuring out what to do with that. And the answer is there's a unique maximal evolution from initial data of Einstein's equation up to isometry, up to the natural notion of isomorphism for relativistic spacetimes. Now, the point here is that in the background of the whole argument is a really important collection of mathematical facts from which we can infer something really interesting about, first of all, what kind of structure Einstein's equation actually governs. It's the stuff that's preserved by these isometries. How we should think about the initial value problem in the context of general relativity. We can think about contrasts between this way of setting up the initial value problem and other theories. Turns out that all metric theories are going to turn out to not have initial value problems in this sense is the thing that I think people are still not totally clear on. But it's true if you write down special relativity as something that's a candidate to be symmetric hyperbolic system, it is not symmetric hyperbolic. It also is subject to the whole argument in just the same way. Teva's going to work this way. Everything is going to work this way. Okay, and so what I'm exhibiting to you is a way in which something that turns out to be closely connected to the application of diffeomorphisms to solutions to Einstein's equation, even though it isn't investigating the symmetries of the theory, ends up providing really valuable information that, as a historical matter of fact, greatly informed our understanding of the structure of relativity theory. And I think that I'm not going to do it in interest of time. In fact, that was the last slide. But basically all of the examples, why did I say basically, all of the examples of successful symmetry-based reasoning, you're going to be able to spell out in this kind of way. And you're going to see that there really was some substantive thing that we learned about the world by applying the symmetry reasoning. But in each case, it's going to end up looking very sort of specialized to the case. Okay, I'm done. Let's, okay, Ken, you can ask me a question.
Well, if we don't have time, then.
Well, so what we're supposed to do now is have lunch and then have like a general discussion. So if someone wants to start setting up lunch in these tables here, we can have some questions that are.
Yeah, so I'm thinking back to what you were saying about logic and metamathematics as the theories of what we're doing. And it seems important to me from my own work that these theories are not correct as theories of mathematical reasoning. That our language doesn't actually have the kind of syntax that a first order language does. And what we're doing when we give mathematical proofs is usefully approximated, but is not is not even expressible in terms of giving formalized arguments. And so then I wonder, what does that mean? Because I think then we take these things to give some sort of concept of logical correctness, that what we're trying to do is get logically valid inferences. But that seems to be something that emerges from the theory rather than from the practice itself as it was. And so I'm just wondering whatever's going on in this relation between the theory and the thing that the theory is a theory of seems different from the others, because it's not like us theorizing with a certain physical theory then tells us we ought to make the world behave like that theory, the way that we feel like with the mathematical theories.
But hold on, do you think that there are examples of cases where mathematicians, I know there are cases of people trying to do this,
Yeah.
but I don't think that this is how the history of math has actually gone.
Yeah.
That mathematical logicians come in and say, here's how I'm going to theorize about what you're doing, and oops, you're wrong. You're using an infinitary method, or you're using the axiom of choice, or whatever the problem is, and then convince mathematicians that you should stop that they should stop doing that stuff. I mean, there was a period in the 20s, the early 30s, where that was like a live possibility that like constructive math was going to win and we were going to just throw out a whole bunch of stuff. And then that didn't happen.
Right, the thing I'm thinking is that once people prove something's independent, they now say, we don't need to keep searching for a proof. That the logical relations of first order physical logic are the things that do. And I guess it's important that maybe Gödel didn't interpret his result that way, that he thinks we get these independence results, but that doesn't mean we're done with the question of the continuum hypothesis. But for a lot of purposes, we do take independence results to say, all right, we now have this, no longer have to search for proof because there won't be one. Even though what we prove doesn't exist is a formal object that doesn't necessarily correspond to
Yeah, I mean, look, I think that there's sort of three things to say. One is, I totally agree with you that first order logic is at best an approximation to how mathematical reasoning works. Kind of you might think like a toy theory of how mathematical reasoning works, but in that sense, it's very, very similar to lots of other cases of applied math. The second thing to say is, I do think that there are like interesting nonlinear things that are going to happen when you're sort of doing math yourself as a reasoner, or you're just going to start questioning whether what you're doing makes sense in light of what you're doing. And I agree that like just that sort of a special case that's not going to come up elsewhere has and will continue to have interesting effects. The third thing is, like, I think as a historical matter, some people do still try to prove the continuum hypothesis, not from ZFC, but from ZFC plus other stuff. And there's another interpretation of why people stopped trying to prove the continuum hypothesis, which was that the efforts to prove the continuum hypothesis in the 20s were tied up with Hilbert's program, and that kind of ended because of Gödel. And so it somehow doesn't have quite the same motivation from a sociological perspective in math. So, yeah. David.
That's wonderful. On the symmetry part, I mean, I think I agree with nearly everything you're saying, given the initial definition of symmetry as structured learning maps. Then I want to know how I kind of relate that to a dynamical symmetry, where the symmetry can be transformation of a relatively motion invariant. And I mean, because at least as I see symmetry-based reasoning, huge evidence in situations where we have a symmetry in the dynamical sense that's not a structure. And then we do something about it. I mean, why do we use U1 to gauge theory? Well, one of the places is that is an analogy of the Leibniz space-time argument where there was a mismatch between the dynamical symmetry and the structure.
Yeah, so I agree with everything you're saying. It's a long story. Unfortunately, I only have 45 minutes and it's an hour. So yeah, I mean, look, you're right. Dynamical symmetries, in my view, are connected up with these questions about symmetries of the theory. And I think that, in fact, in all cases where we have things that we want to call dynamical symmetries that we then want to say are like fruitful to reason about in physics, there are ways of capturing the equations as a mathematical object such that it truly is the case that these things are symmetries of the equation. And I also think that in some cases, just as you say, in fact, it turns out that the things we thought for other reasons, but also other reasons about investigations of structure that we think ought to be related to these equations. And we find that, in fact, they aren't symmetries of the equations. Now we have to think, well, how would I change my representation of the equation or the equations that are being represented in order to make the symmetries match? So I actually don't think that, I think that explaining in particular cases how to make sense of equations as mathematical objects in the way that you would need to make this way of thinking go through is kind of time consuming. But I think if the story works out the same way, if it doesn't work out that way, then there's just another notion of symmetry on the table, and I probably wouldn't be able to be quite as dismissive of other parts of the symmetry literature. Thanks. Okay, great. Let's have lunch and then general discussion.